Dr. Lucy Lowe, this is Axiom Mission Control Center. Please call station for a voice check.
Station, this is Lucy Lowe. How do you hear me?
We have you loud and clear, Lucy. It's great to hear your voice up here.
It's great to hear you too, Peggy. So greetings. This is Axiom Space Chief Scientist, Dr. Lucy Lowe. I'm super excited to talk to you today about space radiation and the research that's being conducted on the ISS as part of Axiom Mission 4.
We're looking forward to talking about it, especially Swab, as the radiation guy.
Hello, hi, Lucy.
Absolutely.
Nice.
Hi, Swab. So, Peggy and Suave, it has been a pleasure working with this crew and with all the teams as we expand this global research community that is bringing research into this really unique orbiting lab. So with that, I'm going to jump in and ask you guys some questions. So, Peggy, I'll start with you. I'm going to ask you a little bit about what is space radiation and are humans exposed on Earth?
Well, it's interesting. Space radiation comes from lots of different places. It's galactic cosmic radiation, protons, high energy particles. It can be made up of a lot of different things. But what's interesting about Earth and kind of why we adapted the way we did is because there's a magnetosphere around the Earth that actually prevents most of the radiation from getting to Earth. And so there is some radiation still left over coming in from the sun and from actually from resources in the Earth like radium, just from minerals in the Earth. And so we are still exposed here on Earth, but it's much less than you get if you get beyond the galactic, the Manel radiation belts or the magnetosphere. Right.
Yeah.
Okay, well, that's great to hear that we're mostly shielded from it down here on Earth. And I'm going to ask Suave a little bit more about how you guys are shielded up in orbit. But Peggy, can you tell us a little bit about how space radiation that you guys might be shielded from up there, but also that we get a little bit down here on Earth? What does it do to humans? Can you tell us a little bit about if it's dangerous?
Actually, very high levels of radiation are very dangerous. We have found from research that there's DNA damage caused by the high energy particles breaking up the DNA itself inside our bodies. And that causes things like cancer and other mutations in our genetic code. It also has been found to contribute to cardiovascular diseases and maybe some of your cognition abilities if you have very high levels of radiation exposure. So it can have a number of different physiological effects. So luckily, most of the Earth is protected from the highest levels of that. For instance, if you were outside of the magnetosphere, and a solar particle event, which is one of these high energy events that comes from the sun and the solar flare, can cause really high levels that would actually probably be lethal or very, very damaging to you, make you very sick.
Oh, well, that's no good at all. And it's fascinating how different kinds of radiation can actually be used for therapeutic purposes for example, cancer treatment. So really fascinating the both dangers and advantages of radiation. So, Peggy, can you tell us a little bit about what Axiom Space has done on previous missions to advance research on radiation?
Yes, so there's lots of different ways to protect from radiation. Some is with materials, and we've looked at a study where we were looking at materials that you actually put on your body. Other cases, we're looking at materials that you would put on the structure of the vehicle that you're building to try and prevent the radiation from getting in. We've looked at different types of radiation bricks to prevent the radiation penetration, trying to be as efficient. Obviously, if in a spacecraft, we don't want to send up lead because that's very heavy and very costly. So we want to try and come up with some alternative ways to protect ourselves from the radiation. So a lot of different materials studies have been going on. And we are also on this particular mission, studying a lot of ways of measuring radiation in space to better understand it and know what things are and are not effective for the human being and for the structures. And
Yeah, and that's fascinating. And that's a
property as well today, too.
And that's fascinating. That's a great segue to move over to Suave as well. So Axiom has teamed up with CERN to use its particle accelerator to look at the effects of galactic cosmic radiation on our critical computing systems. And Suave has made remarkable contributions to CERN himself. Now, Suave, you were serving as the lead engineer for the Large Hadron Collider and managing its continuous operations, which is absolutely fantastic. So I'm very excited to hear your expert insights into this topic and learn a little bit more about the research that Poland is doing on this mission to advance and understand space radiation a little bit better. So to begin, can you tell us a little bit about how space radiation is different from the radiation on Earth? Peggy mentioned about how it consists of different particles, but in space, where do these kinds of particles come from? And how is that a significant concern for future deep space missions?
Yeah, exactly. As Peggy mentioned, and Peggy did a great introduction, in space there are different sources of radiation. Our sun is one of the prime sources that sends solar wind and sometimes ejects mass from the sun that are called, these events are called coronal mass ejections or solar particle events. And then if they are directed towards Earth, we all exhibit, for example, beautiful auroras, but this means that the radiation in orbit is quite high. On Earth, we are protected by the magnetic field and by our atmosphere as well, that this radiation collides with other particles and much less gets to us. So sun is one of the big source. Other sources, Peggy mentioned as well, what are called the GCRs, galactic cosmic rays. These rays are coming from outside of our solar system, from different galaxies, different star systems, and then penetrate through our solar system and make it to us as well. So these are, let's say, the main sources. And obviously around Earth, as Peggy mentioned as well, Van Allen belts. These are belts of radiation that are trapped around Earth in our magnetosphere that helps us to shield us to a certain extent, but as well cause problems for satellites that actually need to cross these Van Allen belts. And if we imagine, for example, a trip to the moon, we would need to cross the radiation, Van Allen radiation belts, and then we would be exposed to a much more harsh radiation environment on the trip to the moon, or, for example, in the future to Mars.
Amen.
So it definitely sounds like we need to both understand and protect ourselves and probably our computers and our spaceflight hardware from this kind of radiation. So Suave, what kind of effects might this radiation actually have on spaceflight hardware, including things like computers? Can it interrupt function? What sort of things might happen when a galactic cosmic ray collides with something that is critical hardware for flight?
Yeah, there are so many different effects that can happen. Like Peggy mentioned, there are effects on human beings. There are effects as well on systems. So it can cause, a computer to freeze, to hang, what is called a SEFI, single event functional interrupt. So this is one of the events. Sometimes radiation can impact our chips, our integrated circuits, and cause permanent damage. And let's say the component can just I would say, try and then stop working. So these are other types of events. Sometimes it causes corruptions of memories. So we hold data and, let's say, pictures of Earth, and sometimes certain data are being corrupted, and we can correct them using different algorithms in a software way or in a hardware way. So there is many techniques and many different effects. It's a very, very complex topic, but that's why we need to study and measure radiation to understand its dynamics, and then later on study and test electronics to know how this radiation impacts it. And you mentioned a very good collaboration between Axiom Space and CERN that was established particularly to test electronic components in particle accelerators to understand the behavior of this electronics in radiation environment. And here on the ISS, we brought many different data acquisition systems to understand the complexity and dynamics of the radiation environment here in orbit.
That is absolutely fascinating and so exciting to hear of the work that Axiom Space is doing with CERN, and definitely really critical to understand what is going on to these computer systems, and fascinating to learn about how there are different software mitigation things that we can employ to protect from radiation. But what are some of the physical ways that we can protect from radiation? Peggy referred to some of the different materials that we could use. She talked about lead, but obviously that's really heavy. And very difficult to launch up to space for the amount that you might need. So what kinds of materials are good for blocking space radiation? And what kind of research is being conducted on AX4 that might be able to protect us in future for long duration and deep space exploration?
Yeah, this is also a very broad topic. Obviously, you can design electronics in a certain way so it doesn't fail, or you can apply protective shielding to decrease radiation to acceptable levels. And then the variety of materials is big, as in space we don't like lead because it's heavy. It protects well against certain types of radiation, but not all of them. And being quite a heavy material is maybe not the most adapted. We used a lot of different other much lighter materials, polymers. Obviously, our International Space Station is first shielded through its structure, mechanical structure, and let's say first shell that is made of aluminum and different alloys. And then later on in, for example, where we are in crew quarters, there are polyethylene blocks that allow to capture certain type of radiation, certain energy, certain particles, so they do not make directly to our bodies or to the systems that are here around us, as you can see behind us, racks of electronics where we perform science.
Fantastic, yeah. And I'm guessing that mission planning also plays a fairly important part here, because as you referred, Suave, then when there are sunspots or coronal mass ejections that create these beautiful auroras here for Earth, they put you right in the way of those paths of plasma as they come from the sun. So I'm guessing that the mission planning also helps minimize the exposure, so to get you into the right places at the right times.
Yeah, that's also quite a broad topic. Mission planning is crucial. Now we are in the solar cycle, what we call the sun has an 11-year period cycle that exhibits high activity of the sun and low activity of the sun. Obviously, we cannot change that. We are on the ISS permanently for over 20 years. Now we are in the highest activity of the sun, but so we face a certain risk of these coronal mass ejections, solar particle events. But on the other hand, this is the best moment to mitigate galactic cosmic rays that do not penetrate our solar system and they do not make to us. And actually, galactic cosmic rays are the most dangerous for our DNA, for us as human beings, and because they can cause really big damage to the cell, being very high energy and extremely ionizing, meaning that they can really break up our DNA strands that we cannot later on repair. So this is mission planning is important, and then knowing and understanding that complexity is important for system design as well as for dosimetry for astronauts.
And also for some of that, just measuring the dosimetry, knowing when the levels are going up, can allow someone to get into a safer location. For instance, on the station, you could go to the more shielded areas. And so future spacecraft can also, if they have a way to measure and predict, they can do mission planning that will allow them to help themselves, protect themselves.
Yeah, fantastic. So a really complex situation then. And it sounds, from what I hear, Suave, there's actually a Polish radiation research monitoring experiment taking place on AX4. So can you tell us a little bit about what the Radmon on ISS experiment is doing in terms of monitoring the radiation and what the plans are for that in future?
Yeah, sure. I actually got this radiation monitor out of the box. We will be installing it quite soon. You can see it floating just in front of us. And then this is a radiation dosimeter that was initially designed at CERN, and through the CERN knowledge transfer, made it to a Polish company that commercializes this product now. And the main idea behind that is it measures different types of radiation, but this is just the first step of research. The further steps are to implement a much more compact version of that box into satellite systems, space stations, to do a direct measurement and potentially generating certain signals to protect hardware or protect stations. So to have a real-time measurement system that later on helps guiding certain decisions. So for example, let's imagine there is a solar particle event going towards a big communication satellite that we would like to detect. Such a device can detect increased radiations and can switch off the satellite, helping it to pass this time of higher radiation, and then automatically powering on the full satellite in a safe way when this radiation is below a certain threshold.
That is so cool. So this kind of research being done on the ISS right now is really paving the way for some advanced spacecraft design, not just for human crewed missions, but also for satellites and all kinds of hardware in space in future. So that is so exciting. So I think we're almost out of time for today, but I really want to thank you, Peggy and Suave, for joining me today. These efforts for space radiation research are so important to make really significant advancements in this critical field. And you guys are paving the way for scientists and researchers and engineers, not only on Earth, but also in space in future, to not only understand space radiation, but also ensure the safety and success of future space missions. So thanks for all your work, and we'll see you back in Houston.
Good to chat with you, Lucy.
Thank you, Lucy. Bye-bye.
That concludes the event. Thank you to all participants.